we have Ananda Roy who will tell us about variational quantum simulation of an anyonic chain. Please take it away.
Thank you. Thank you for the invitation. And it's great to be back here. So my talk is based on this preprint here. And so I'm a bit embarrassed because I kind of will give some background that already was spoken by Michael, but I guess repetition is key to education, right? So at least I recap every time I give a lecture in the course. So the idea is that there exists such a thing as a complexity hierarchy that is currently believed. And it turns out that there is a class of problems that can be easily solved on a classical computer. This would be like a deterministic Turing machine. And this set of problems is called P. It stands for polynomial time. And as I guess all of you have heard somewhere or the other that there is such a thing for quantum computers as well. And it's believed that the yellow egg is bigger than the green circle, although there is no proof for that. But it seems to be like, and the BQP here stands for bounded quantum probabilistic. And then there are bigger, more complex problems. And so there are the problems that are difficult to solve on a classical computer. But they're funny problems that if you give someone a solution, then they can check if it is correct or not. And those are the ones that are in NP. And that's why P is actually inside NP, because then you could actually check the solution by solving it. And then there is an analog of NP for quantum problems, which is what was coined by Kitaev, which is called the quantum Merlin-Arthur. And it's also believed to be bigger than NP. And then there are more complex problems. We don't need them. And so our interest is, of course, in the part of the yellow, which is outside the green. And we seem to think that there are lots of problems of practical interest, which lie there. So the fundamental workhorse is really the quantum Fourier transform, which lies at the heart of Shor's factorization algorithm that I'm sure you have heard about, and the phase estimation of Kitaev, which is used extensively in quantum simulation, which is one of the biggest applications in physics. And this is not to say that there are not interesting problems in P. As you know, free fermion models are examples. Normalizer operations of Pauli group, they are also very interesting problems. They lie within the stabilizer formalism. So they are also in the P, but our interest is, of course, to go outside P. Now, it's a bit hard to have an intuition for complexity. At least I find it difficult to explain this in simple words. So the only way that I found was to provide some intuition, which is somewhat incorrect, but it still works most of the time. So the idea here, and here complexity is really referring to quantum state complexity, not process complexity. And the idea is that if you have a target state with more entanglement than between regions, then that's more complex. And you can intuitively think that you have a quantum circuit that's going to build up the entanglement as it's implemented. And assuming that there's some amount of locality in the geometry of the quantum circuit, you can imagine that the depth will grow as you need to introduce more entanglement. And so if you believe this, and there are counterexamples to this, but if you believe this, then for pure states, von Neumann entropy is a quantitative measure. And so you can easily, for a bipartitioning like this, you can rapidly write down what is called a Schmidt decomposition. This is any pure state can be written in this form, where you can write down sum from L to 1 to omega. Omega is the so-called Schmidt rank. And SLs are the Schmidt values, and the states are the orthonormal basis state for A and B. And why do we care about this? Well, because the omega essentially determines the von Neumann entropy in some form. And if you have some reason to believe that there is some bound on the entropy, let's say because of the finiteness of correlation length, then there will be an induced bound on omega, and this will put a bound on the circuit depth. And this is kind of the logic that one could use to say that, well, the ground states of gapped one-dimensional systems are easy to solve on a classical computer, or easy to simulate up to exponential accuracy. And because the Hastings proved a bound in 2007, that the entropy is upper bounded by some power of the correlation length. And similar arguments go for one-dimensional critical models. And I guess you heard some of these statements also just now before about what is hard, what is easy. And so the statement is that the entropy of these critical one-dimensional models, they grow often with logarithm of the system size for low-lying states. And so this means that the Schmidt rank, the omega, will go as L to some power. This exponent has sometimes some universal meaning, but for now it's just some positive exponent. And so these are states that are relatively easy to simulate. And the statement is that quantum simulation can be needed for phenomena that involve states where the entropy itself grow with some power of length. And so then the number of states needed to store this information would grow exponentially, and that's the exponentially large resources. And there are counterexamples, so don't take this too literally. But as you just also saw in the previous talk, that quench dynamics is a paradigmatic example of where such things arise, even in one dimensions, where the essentially be one in the generic case. And they're also for equilibrium characteristics of two-dimensional models, these things also arise, and you can relate this back to then the so-called area law of entanglement entropy. And my goal here is to talk about some realization of anyonic chain ground states using some hybrid quantum classical algorithm. And I will just say it up front, there is no claim of any supremacy or anything. So it is just that these anyonic chains don't really arise in realistic solid-state systems or condensed matter systems. This is a way to realize them. That's all I have to offer. I find them interesting enough to do this, but there's no supremacy. Most likely there's a lot of pain. But so what are these hybrid quantum classical algorithms? So the idea was that initially when the quantum algorithms were proposed based on the quantum Fourier transform, the workhorse was the phase estimation. This phase estimation was used for demonstrating the superiority of computing power of quantum machines like factoring and quantum simulation. But the difficulty is that the phase estimation requires a lot of overhead. So it requires long distance connectivity. There are controlled unitaries that have to act on large registers of qubits. This is hard to do, at least right now. And so there was some idea that was put forward, and how good it is, it's still, I think, up for debate. The idea is that you could combine the power of classical computers with the quantum computers. And so the schematic that is often advertised is the following. Imagine that you want to find the ground state of a complicated Hamiltonian, and which can be written as a sum of some terms. And then this picture from Peruzzo et al. Says that you can come up with a parametrized quantum circuit. So imagine that you have a quantum computer that is not very good, but it still can apply a bunch of gates. And then you have to figure out what gates to apply. And figuring that out is an iterative optimization process. But what you will do is to apply those gates, measure the expectation value of different terms of the Hamiltonian, add them on a classical computer. Then you will apply some kind of feedback loop where you will perform some optimization problem on a classical CPU. So there are two non-trivial steps here. One is how to figure out this parametrized circuit ansatz. It's a very non-trivial question. If you conceptually think about it, you're trying to find a unitary rotation of n-particle system from an unentangled and low entangled state to a highly entangled state. And this is not exactly something that tensor network algorithms like density matrix renormalization group is a big expert of doing. This is a different question. And at the same time, the optimization problem is also quite hard, because if you want to look at circuits for many body optimization questions, then there'll be many parameters, and you need to really have a lot of computing power to solve this optimization problem. And so here we came up with some simple ideas to tackle these. And so the first idea was to come up with a circuit ansatz that does not care about the target problem. This was something that was somehow, maybe because it was too naive to think like that, but somehow it was not there in the literature, where we could just say that just like in a quantum computer, you learn that there is a universal discrete gate set that could be used to simulate any arbitrary unitary rotation. And here our idea was, can we not have a universal circuit ansatz whose parameters depend on the problem, but not the ansatz itself? And it seemed quite reasonable. And so the approach that we took was to apply n layers of unitary operators. These unitaries are different from layer to layer in terms of the parameters of the unitaries. but the generators of the rotation, they are the same. And for now, we thought of just using the all 1 and 2 qubit rotations for the layer unitary. So the layer 1, for instance, and layer 2, and so on. And we will impose geometric locality. I think not all of us are lucky to have such wonderful quantum machines that have arbitrary connectivity. And so for us, we were working with IBM's machines, and they have definitely some advantage of using local gates. So this is our breakdown of the unitary. So we have a layer unitary that we break up into nearest neighbor SU4 unitaries. These are just the general unitaries that act on the state space of 2 qubits. And then we use some 18th and 17th century mathematics to just compress them into some ellipses that I showed just now. So the first thing is the Cartan KK, which is the decomposition of the SU4 unitary into single qubit rotations and some SU4 entangler. And the single qubit rotation, as you learn from quantum mechanics courses, it's the usual Euler angle decomposition, so there is nothing new there. And this one you may not have seen before. It is the SU4 entangler that can be broken up into 3 C knots and some single qubit rotations. So the different rotations used here are shown as legends. So you see at a conceptual level, the 2 qubit unitary operator provides the entangling power here, here, and here. These 3 C knots give rise to entanglement. All the others are just local rotations of single qubits. And when the dust settles, then you get some ellipse like this, which has essentially 10 parameters. So these are the 10 parameters we need to optimize per ellipse. And you can actually throw away that one last parameter right there, but that's something that to keep it is not a big overhead. And now this is still a lot of parameters to optimize. As you can imagine, each layer has then 10 times the circuit width number of parameters. And so we can impose symmetries through the circuit ansatz or through the cost function like the Hamiltonian. So at the very basic level, you can think that if you are looking for a translation invariant ground state, then start with a state that's translation invariant, let's say all spins pointing up. And then if you want translation invariance upon translation by one lattice site, then just make sure that all the squares or all the ellipses are just the same. So there'll be 10 parameters. If you want translation invariance by 2 lattice site, then there'll be 2 such ellipses that's just 20 parameters. So it's in per layer. So that's much better than having 20 times the circuit width. But even then, it's quite a non-trivial task to update to solve this optimization problem. So here is the optimization strategy that we have. And so typically one can just use some standard optimization routine like the first order gradient descent. This is the update that you would do, which is essentially updating the set of angles by which the rotation is happening iteratively. T+1th iteration depends on the tth iteration in this way. L is the expectation value of the Hamiltonian. But this kind of assumes that the space of angles over which distance is being measured, as you go from the point theta t+1 to theta t, this space is Euclidean. This update assumes that. But we know that the state space of wave functions has curvature. Can we somehow update in a way that keeps track of the curvature? And it turns out there's a very elegant formulation based on the quantum natural gradient that does that. So you see the updates are almost the same, except that there is now an extra factor of G, which shows up. That's the so-called Fubini study metric that essentially is used extensively for computing distance between states in a state space. And it also turns out to be the real part of the quantum geometric tensor. This is the form of the geometric tensor. And during the optimization process, we are going to calculate this by computing multi-point correlation functions. And I should say that this is an expensive thing to do. First order gradient descent is computationally cheaper, both for classical and quantum computers, compared to the quantum natural gradient. And it is not needed for this circuit ansatz to be useful. the data that I will show is actually relying on first order Adam type gradient descent, which is a modification of the first order gradient descent. And it's somehow funny that when I was first discussing this and with Simeo, it somehow came up that this Fubini study metric is extensively used in different fields for quantum Fisher information, which has extensive application in not just metrology but also multipartite entanglement detection. So it's like a unique, it's a very important concept that is something that at least I did not learn in my quantum course in undergraduate level or graduate level, but it's somehow something that's ubiquitous across different fields. And it is this approach that we will take. We will use the Fisher information. Okay, so now with this knowledge, we are going to just implement the quantum circuit to realize ground states of anyonic chains. And so these are generalizations of spin chains. You can think of them as just like if you think of a spin chain that has tensor product Hilbert space. Here we have something a little bit more fancy. So here not all states are allowed. That's just one way to just say that there are some underlying symmetries that prevent you from writing down a tensor product Hilbert space. And the underlying structure is given by, just like you have for spin chains, you have groups. Here you have fusion categories. And sometimes for these anyonic chains, which are determined by some fusion category that obeys some consistency relation, like the pentagon equation, here what we will do is to look at some certain class of these anyonic chains, which were discovered in a totally different context by Andrews, Baxter, and Forrester in 1987. And these are very nice models. They also go by the name of restricted solid-on-solid models. They happen to be integrable, so we have a lot of control over these models. And the idea is that each site is a p-level spin, and the states are determined by this diagram. So here it's a state line. It's called a Dynkin diagram. It can have other structures too, but conceptually it's very simple. So the idea is that if a site has a given state, the next site can have states that are connected to that state. Okay, so if you have a site in the state 1, the next site can be only in the state 2. It cannot be in 3 and 4 or any others. Okay. On the other hand, if you have a site in state 2, then the only allowed ones are 1 and 3. It's just determined by the adjacency matrix of that Dynkin diagram. And yet another example where if you have a site in state 3, you're allowed 2 and 4. And now discretization is quite simple. So what you do is you discretize the p-level spin into qubits. You need log base 2 times of p qubits. Simple examples, p equals 3. This would have, you need 2 qubits per link. You can have these 3 states, for instance. If you have p equals 4, you can just use the 4 states right here. And what is quite interesting is that there is some even odd effect in the states in the allowed states across the chain that you can capture by measurement of ZAZB. So for instance, if you have the first link in an odd state, you can show that the next one will be in an even state. It just follows from the structure of the Dynkin diagram. And of course, if you can measure ZAZB and capture this signature, that's of course a very tangible thing to do on a quantum simulator. And in general, the Hamiltonians have lots of nasty looking couplings because they use projectors. So we don't need to write down the explicit form. I wrote them in that paper, but it's not so important for us. Is the model clear? Does everybody understand the model? I'm kind of ranting on without any interruptions. Interrupt me. Okay, so let me show you some data. This is done with noiseless simulation. This is Adam optimization with about of the order of L circuit depth. So I analyzed Hamiltonians with fixed and periodic boundary conditions and at the quantum critical point. These are interesting models that can actually be tuned to be critical, or you can have off-critical behavior. And the boundary conditions also play an important role here because these are very, very delicate models. You will see this now in how the state space will change depending on what boundary conditions you impose. And for the experts, this P is an index that I have been using here, and they actually are quite it's quite significant. So it turns out that the states that I got are the ground states of the lowest 5 non-trivial minimal models of conformal field theory with diagonal modular invariance. So these are the so-called A-type models. It's not probably that important for this talk, but this is quite interesting. Yes.
So this you have on each side E levels, but what is this drawing?
What is the
line?
N?
Like
Good.
you have,
Yes.
on side 1, you're gonna have a superposition of all E levels, right?
No. That's a good point. So here, what I'm showing you is the L is the system size. I have 24 spins. Okay, I have 24 qubits. The quantum simulator that I'm thinking of has 24 qubits, and then depending on what P is, the number of anyons is either 12. For P equals 4, there are 12 anyons. For P equals 5 to 8, there are 8 anyons. So each anyon is discretized into log P qubits,
that's
right?
clear.
And that's so the N is the layer index. So I need this many layers to get this much energy uncertainty in the ground state. Good, thank you for asking me. Any other questions about what I'm showing here? And this is something that I find at least quite nice, that the circuit ansatz did not change, the system size did not change. I just changed the Hamiltonian, and I get different CFTs. So that's somehow, I think, how it should be somehow, I think. And I was talking about the even odd oscillation. So this is P equals 4 for the experts. This is a tri-critical Ising model. And so it has 18 qubits. So there are 9 anyons here. And also for the experts, these 9 anyons can be mapped to the Fibonacci anyons that people know. And the statement is exactly like the even odd effect that I was discussing before. You indeed see by computing the ZA, ZB in the neighboring sites, you see the exact -1 +1 type oscillation that you would expect from the Lincoln diagram itself. And it's even more interesting to look at the occupation probabilities. So once you have the state, you can measure what is the probability of getting the first anyon to be in state 1 or in state 2 and so on. And so here I use fixed boundary conditions. So I have the boundary anyons in state 3. Okay, that's fixed. And now if you look here, for instance, here, if you have state 3, the nearest neighbors are 2 and 4. And indeed, I see non-zero probabilities in 2 and 4. There is no 1 here. But then on the other hand, here, there is a 1 and 3 because these states are in 2 and 4. So it's exactly like what you would expect from the adjacency matrix. It shows up in the probability of the occupation. And you can change the boundary conditions, and this will change the occupation at the boundaries, which helps in really analyzing the anyonic nature of the physical states. So this one hopefully will help in driving the point home. So this is P equals 5. This corresponds to the tetracritical Ising model, and there are also other operators that one could measure, but I'm going to just focus on the occupation. Here I have fixed the boundary spins to 1 and 2. See, when you have 1, you're only allowed to have 2. And indeed, here you exactly have 2. But here, when you have 2, you can have 1 and 3. So you again see that exactly the states that are truly allowed are the ones that are showing up in the occupation probabilities. Now, this is, of course, all noiseless, right? So this is all noiseless. And so the question, of course, is, can we do something with noise? So this is our quantum simulation experiment. It's a very modest effort. So we used IBM Kingston and used the Ising case, not even the tri-critical Ising, but the Ising case. And so we had found out that there was some nice set of Hamiltonians that interpolate between fixed points of conformal field theories with defects for experts on Kondo models. This is essentially interpolating between the 2 fixed points or in the Kondo model. So where there is a Kondo temperature, and you essentially change that Kondo temperature and probe between the point where the spin disappears and where the spin is there. So this is kind of the the model that we analyze. So there is a ring, it's a transverse realizing model, but with some perturbations. So that's the different couplings there. There's some inhomogeneity in this Hamiltonian. And the 2D CFT with the defect line is being shown here. And then we use some kind of parametrized circuit ansatz to get the ground states. And I guess the data that we are moderately proud of is this one, where you see that the orange curve is the one without defect. So there is no impurity. And this is the case when you have a defect. You see that the dramatic drop in the correlation function as you go across the chain. The location of the defect or the impurity is exactly. And it's funny that one of the first works on this topic was actually done by Ian Affleck and Masaki Yoshikawa in 1997, well before even topological symmetries were fully appreciated. And we are implementing really that model here. And you can do a few more things like computation of topological symmetry, operator expectation values, and so on. I won't go into too much details, but you can see the agreement between the exact number that you expect and the experimental data there. It's quite good. And so we used the standard noise mitigation approaches, ZNE, dynamical decoupling, and so on. And it seems like what we are doing is working at least at the level of the system sizes that we are analyzing. I guess, how many minutes? 3, 4, okay, good. So let me, for once, I will be able to tell you about the outlook. So it's about the whole motivation to do all these calculations is really to get to something that Nielsen had proposed many, many years ago. It was to kind of come up with an idea of bounding quantum process complexity. And so Nielsen had worked out the general unitary case when he had said that any unitary operator can be approximated in order n to the 6 times d cubed, 1 and 2 qubit gates. N is the number of qubits, and d is a distance. As you can imagine, the unitary operators also form a manifold, and there is a well-defined measure of distance, and you can compute the distance between the identity and the desired unitary. And with these variational approaches, we seem to be able to get close, if not hitting the bound of Nielsen's Nielsen's bound. And approximately, because exact computation of this relevant geodesic is a hard problem. And what we did for some set of unitaries was to use automatic differentiation to really get close to at least Nielsen's bound. And so our hope is that we'll be able to get to the real lower bound for the approximation of quantum processes, general quantum processes with hopefully numerical techniques. Okay, good. Let me stop here. So some of the work was done in collaboration with Robert Koenig at Brookhaven and my 2 students at Rutgers who did some of the Ising simulations, experiments, and numerical work. Thanks.
Minutes for a couple of questions.
Yes.
I have a technical question. So what role do the Dinkin diagrams and the adjacency matrix playing here? So I know that like you have families of anyons associated with modular S matrices, and you can calculate fusion rules from that.
Right.
But I don't understand the connection here. So what is the adjacency matrix telling you?
So the adjacency matrix tells us what the partition function of the model would be if you put it on a torus. That's the
I see. Okay, it's just the combinations of characters.
Exactly, the character combination is determined. So the A-type one has this line, so it's diagonal invariance.
Okay.
And then D-type would be like pots or
Right.
tricritical pots, something like that. Yeah.
One contract things, but you said you've got the one mental gradient using what method?
I used, so for the work, the data was not done, not taken using that, but in general, you could compute multi-point correlation functions.
So for the actual IBM experiment, how do you measure the quantum mental gradient?
I don't have slides for this, but the idea is to apply controlled unitaries using an ancilla. So the ancilla qubit then is subsequently measured. So you actually apply controlled unitary of the so here so essentially you can think that this will be a 2-point correlation function. And these 2-point correlation function, you apply the relevant controlled operators that then measure the ancilla that would give you the 2-point correlation. It's the same trick that we also used for, it seems to be quite useful, this trick. For here, this data on the actual quantum machine, we applied the controlled braids. You can see the braid operators here. These are, it's in the general context, they are fancy braid operators. Here, they are just unitary equations. And you can just apply controlled unitary, and then it works right away. Again, the last qubit is the ancilla. It's using exactly the same idea here.
Yep.
Yeah.
I have a bit of a math question. What is the contour again?
I didn't show you. I didn't show you because it was complicated, but the Hamiltonian, well, you know the transverse Feelising Hamiltonian, right? So the Hamiltonian is the XX plus Z, this kind of thing, right? But the thing is, there's the true Hamiltonian, there's no whiteboard. So there's true Hamiltonian is written in terms of what are called Temperley-Lieb generators. So the Temperley-Lieb operators are essentially 1 over square root of 2, 1 plus XX, and 1 over square root 2, 1 plus Z for the Ising model. And now for the other models, there are more complicated expressions for the Temperley-Lieb generators, but then the Hamiltonian is always sum over Temperley-Lieb with the ferromagnetic coupling. And the ferromagnetic gives rise to the minimal models of conformal wave theories, and the antiferromagnetic models give rise to the parafermionic models. They have different behavior, different partition functions.
Okay, there is another question. Oh, okay, so I think we can thank Ananda.